let's learn about trigonometric substitutions. So in your integrand, you'll run into terms that look like this, where a is some constant. And we'd like a way to simplify integrals with these expressions. I mean, these could be raised to certain powers as well. So something that we could do is change variables, okay? This is sort of like the inverse of u substitution. In u substitution, you wrote u in terms of x, and what we're going to do is write x in terms of theta instead, okay? And it's really the same concept. I mean, integration by substitution was really a change of variables, and here we're doing basically the same thing, changing variables, except we write an x of u or x of theta instead of u of x, okay? So if you have a term that looks like this, good idea is to go ahead and use x is equal to a sine theta. And notice this does come with restrictions. Theta should be between pi over 2 and minus pi over 2. And sine theta, well, that can be greater than 1, so x cannot be greater than a. Right? The absolute value of it cannot be greater than a. So you are restricting the values of x that you're integrating with. Why it would be useful to use x equals a sine theta here is because once we plug that, so once we take that x and plug it in, okay, we get this expression. We could write these two separate terms now as a multiple of these two terms, a squared cosine squared theta. Similar reasoning will give you x equals a tan theta for a term like this. And again, what did we buy with all of this? Is that we could write the sum as a product, okay? And a secant for x when you have a term that looks like this. And again, we could write the sum in terms of a product. Now, there are certain right triangles, just like we did with u substitution, when you wrote back the integral in terms of x. Well, these triangles are going to be useful when we have to write back our integrals instead of writing it in terms of theta, to write them again in terms of x. So let's take a concrete example. So we have this 16 minus x squared term raised to the power 3/2 in the denominator. So you could think about it as raised to the power negative 3/2 if it was in the numerator. And that 16 minus x squared, well, that follows this expression here if we choose a is equal to 4, okay? So that's what we'll do, and we'll use x is equal to 4 sine theta, and dx would then be 4 cosine theta d theta. And let's see what we earned with doing that substitution. So we'll have this 16 minus 4 sine theta squared in the denominator. The dx is 4 cosine theta d theta. And now we could factor out that 16. Okay, that's why you choose x is equal to 4 sine theta. And once you factor out that 16, well, you have a 1 minus sine squared term, which you could write as a cosine squared. Simplifying, we get d theta over cosine theta d theta. And that's secant squared. And we know that the derivative of tan theta is secant squared. And so just from knowing the antiderivative there, you can compute that integral. And again, the big deal here is that we were able to, instead of having a difference there, and u substitution would not have helped us, right? Because you don't have a x dx term up there. But we can't stop there, right? Because our integrand was in terms of x. So how do we get back this? What do we substitute for tan theta? Well, the substitution we made was x is equal to 4 sine theta. So we're dealing with this triangle right here, the x equals a sine theta triangle. And so what's tan theta? Well, tan theta is opposite over adjacent, okay? And so you have tan theta is equal to x over the root of 16 minus x squared. And so you just substitute that back for tan theta. And here is your final answer. Let's do another integral. So this time we wish to integrate this 1 plus 4x squared term. And notice that none of these really fit the bill because all of these x's have a coefficient of 1 in front of them. That's all right. You could always massage these integrands and rewrite them in a way that's amiable to the expressions above. And so we could factor out a 4, and we'll get 1/4 plus x squared. We then choose a is equal to 1/2. Okay, so a equals 1/2. We'll do the trick. We'll take out that root 4, which is just 2, and there it shows up there. And now we have a term that does fit into the expressions that we have above. And let's take a look at which one. Well, that's the a squared plus x squared. So we're going to make the following substitution. X is equal to a tan theta. And we're going to take advantage of this trig identity to write the sum in terms of a simple product. And so we let's go ahead and do that. So x, a is 1/2, and x is equal to a tan theta, and so 1/2 tan theta. Dx is secant squared d theta. And when we do that, again, we get to this secant squared here is coming from dx, but then we get to we reach this term here, and 1 plus tan squared theta. Well, that's just secant squared, right? And then we're square rooting the secant squared. Okay, so 1 plus tan theta, this here is that here is secant squared theta, and the square root of it would be just secant theta, and so you get a secant cubed theta term in there. There are several ways to deal with it. Here I do it with integration by parts. So I'll peel off a secant theta from here. Okay, and the remaining term is a secant squared theta. Okay, but secant squared theta is just the derivative of tan theta, right? So this here, this whole thing over here was just secant squared theta, and I'm rewriting it in terms of a derivative. In other words, I am factoring out a derivative, okay? And why am I doing that? Because I'm preparing to integrate by parts, okay? And then I want to move the integral from the tan term to the secant term. And how do I do that? Well, as we looked at in the integration by parts, I'll have a secant theta, tan theta. That's my boundary term. And I pay the price of a minus sign too. The boundary term is minus sign. And now I get to put the d theta on the secant theta. And taking the derivative of the secant theta, I get secant theta tan theta. That's the derivative of secant theta. And so this here is going to be secant theta tan theta. Okay, and you'll see that you end up with the expression that you see over here. Now, if you wanted to do this with the typical u dv notation, feel free. This here would be your u, okay? Or let's put it on the this one here. So this here will be your u, and this here will be your dv. Okay, so you could also use the notation that you're used to. Okay, so if u is secant theta, then du is going to be secant theta tan theta, and if dv was equal to secant squared theta d theta, well then v is equal to tan theta. Okay, and so that's the typical, that's sort of the more formula based integration by parts. But once you get used to the other notation, I find it just easier to write the terms this way instead of getting distracted with a table on the side. So, okay, we'll end up then with that expression. And instead of tan squared, we're going to substitute for tan squared secant squared minus 1. Okay, that's a trig identity there. And what do we do after that? Well, you have a secant cube theta term and then a secant theta term. And wait a second, secant cube, didn't we run into that somewhere? Yeah, we did. We ran into it right here. Okay, and so we're going to use another trick now of solving for the integral of secant cube theta d theta by algebra. Okay, and so what I do is recognize that this is the same as this, and I solve for that integral now algebraically, and I end up with this term here. Okay, and so now that I have the integral of secant cube theta d theta, what am I going to do? I'm going to start back to where we stopped over here. Now I have this integral. I solved for it algebraically. I ended up cyclically returning back to it. That happens with integration by parts. And, I end up with this expression, and I solved for what the integral of secant cube theta is. And so I end up with this final expression here. Now, what do we do? Well, the substitution, we can't stop here because we do need our integral in terms of x now. And so what do? We look at the triangle that we used, which was this, okay? And so you'll have, for example, cosine theta is adjacent over hypotenuse, which means secant is hypotenuse over adjacent, okay? So you'll have secant being the hypotenuse over the adjacent, and looking at that triangle there, so you'll get secant theta is equal to this, right? And you'll have that tan theta. Well, what does tan theta look like for this? That's opposite over adjacent, or 2x, okay? And so you get these expressions that we see over here, okay? And I mean, notice with the secant theta, I mean, we did have an a of 1/2 that we put back in terms of this 4 there. Okay, so we put it back into the square root. And you do get these expressions. And then from there, you substitute them back. And, notice here that although I kept my bounds, I removed them when I started working here. And the reason being, I didn't want to solve for arctan of 0 and arctan of 2 or 4, right? To change the bounds in terms of theta. And we're allowed to do that as long as we return back to the expressions with x. And so I do return back to the expressions with x, and I do return my bounds. And when you plug in your bounds, you will get that result there. So this was a fairly involved integral. I would not feel bad if I did not see that I had to go down this route from the beginning. Very few people could say that they have seen that, okay, right when they looked at it. But with a lot of sweat, you eventually get there, and that's just one more problem that you practiced, okay? And there's a lot of that in Calc 2 because you have a multitude of integration techniques. Well, let's do one more, and this time with secant. And we take a look at that, and well, it doesn't quite look like any of these terms, right? I mean, these are x squared terms, and there's an x. Well, what do we do when we want to change, a polynomial and then just write it in terms of like x minus something squared, right? In terms of a perfect square, instead of having an extra constant times x. Well, we complete the square, okay? And if you complete the square, we have a 4 there, so we know that, we're going to have for our perfect square, a term like this, and that 2 times that term needs to equal this term. And so with some work, you figure out, And we did do a more in-depth completing the square example before, but with some work you'll figure out that this is the expression for completing the square. And then you use u substitution, and well, now you do have u squared minus 9, and that does look like this, okay? And so we're going to do the substitution x is equal to, or u is equal to secant theta, okay? So we completed the square, did a u substitution, okay? And then we're going to do a trigonometric substitution, okay? So we did several things to complete this integral, just like we did it in the integral above. And so now you'll have this 3 secant squared theta in for u. And again, what does that buy you? Well, now you could write it, and you'll get inside this square root, you'll get a 9 tan squared theta, okay? Which, and again, that came from using the identity for secant squared and tan squared. And so now you could simplify this expression, and you have a secant theta down here and a du that looks like that, okay? And notice here the secants will cancel, and you get a tan squared theta. Well, how do you deal with that? You could rewrite that tan squared theta in terms of secant squared theta, which we do know the integral of secant squared theta. It's tan theta. That's just from knowing the antiderivatives. And something to notice here is that we did change the bounds. So above, I returned back to x before plugging in the bounds. And here I'm going to go ahead and change the bounds. It's straightforward to do, because when u equals 3, secant theta equals 1, which corresponds to theta equaling 0. And likewise, when u equals 6, secant theta equals 2, and that corresponds to secant theta, or theta being pi over 3. Okay? So that was easy to do, okay? Because these sort of common angles of for 0 or pi over 3, we know. And so we did that substitution, and we end up with this term here, and our final answer after evaluating is 3 is equal to is 3 times root 3 minus pi. And I'll go a little bit more in depth with that substitution here with the bounds, just because we have not seen that. So you'll have 6 is equal to secant theta. Notice that means secant theta is equal to 2. Well, what is secant theta? That's 1 over cosine theta is equal to 2, which implies cosine theta is equal to 1/2. And, well, we know what angle corresponds to a half, right? That's the that would be cosine of 60 gives you a half, or pi over 3. Okay, and so you get theta is equal to pi over 3. And you do a similar thing with the 0. And so that's how these problems work. Again, it's really just change of variables. These integrals were quite involved because we needed several techniques to get a hold on them, but we did at the end. And we also looked at 2 ways to deal with the bounds. One is to substitute back the expression for x and then just deal with the original bounds. The other is to change the bounds based on the substitution. And so we also considered looking at the right triangles in order to substitute back an expression for theta once we integrate using the d theta.